Hello, my name is Mr. Rogers, and you're watching the video lecture for Properties of Sound, Section 2-2 in our book. So, today, guys, our first page here is just for our lesson objectives. You do not have to write these down. So today, our goals are to describe how the basic properties of sound are changed, how we change the pitch of sound, how low or how high it is, and also to be able to explain the Doppler effect. We'll talk more about that here as we go through. So guys, let's get started, right? A lot of things to do today. So intensity. Intensity is the amount of energy that the wave is carrying, like a sound wave is carrying. And so when you think of intensity, you think about how loud something is. So loudness, the louder it is, the more intense the sound wave. This can also be described as amplitude, how we amplify sound waves. This describes how big the wave is based on the amount of energy it's carrying. So the louder it is, the more energy that wave is carrying. Waves carry energy. It's what they do. So we talk about loudness. Loudness is measured in units called decibels. And there's a scale for decibels also. That intensity, we talk about, it's measured on a scale of decibels. And zero decibels would be what you can hear, and 1 decibel would be that kind of range of hearing. In terms of the loudness anyways, the amplitude of the sound waves. Now the pitch is different. We'll talk about that in a minute. But this is the decibels measure loudness, how loud or how intense that sound wave is. And so on this chart here, guys, a couple things. See down here at 0 decibels would be the threshold of human hearing. And, 0 to 10, leaves rustling, quiet conversation, average office noise or classroom noise, right about 40 decibels. Think about ordinary conversations with somebody nearby within 3 feet, about 60 decibels. Now we get to 70 or 80 when we have planes starting to take off. The orchestra crescendo, that high crescendo means getting louder. So right about 100 here, that's where we start getting in trouble too with really the danger zone. See that red starts that danger zone? This can really cause some permanent damage, especially if you're long-term exposure. And so at 100, it's kind of that threshold point. We're over 100. It doesn't take much time to create or cause damage to your hearing, permanent damage to your hearing. At 120, you get the music amplifier. Once you go like 120, 140, here's your firecrackers. That'd be like a jackhammer. Cannons going off. Think of the loudest sounds, the space shuttles launching. Those are up there, and those are just going to rip your eardrum to shreds and permanently cause some damage. So the higher you go, the louder it is. And yes, after around 100, your eardrum's really meant to handle so much noise, and it can really start to cause some damage inside your ear, especially after long exposures at these higher decibel levels. So moving on. That's the idea of intensity and loudness. And the other idea is not just how loud something is, but the pitch or the range of the frequency there, how high pitched or low pitched it is. So frequency, kind of simply put, is the number of sound vibrations per second. How many waves are coming by you, how many sound waves are hitting your ear. And so we measure frequency in hertz. Hertz measures frequency. So 1 hertz would be 1 wave per second, 1 vibration per second. And so to find the hertz, you divide the number of waves divided by the time, divided by seconds. So when you see that symbol hertz next to a number, that means how many waves per second. So 100 waves per second would be 100 hertz. 1,000 waves per second would be 1,000 hertz. Now, some terms we use to kind of talk about frequency is pitch, how high pitched or low pitched something is. The higher the pitch, the higher the sound seems. The lower the pitch, the lower the sound. And there are human hearing ranges. There are certain ranges that humans can hear, kind of like with the decibels down to 0. And humans have a certain range. Now other animals might be lower or higher, but humans have a certain range. And above this human hearing range, we call this ultrasound. We call this ultrasound. And sounds above human hearing are that ultrasonic frequency. So above 20,000 hertz, that's 20,000 sound waves per second. That's the high end. Most of us can't probably do that anymore. Maybe you still can, but I can't. And above that would be, think about dog whistles. They can hear sounds at above the ultrasonic waves. Can hear that. On the other side, we have infrasonic. That'd be sounds below human hearing. So infrasound, infra means below. And that threshold, that bottom threshold, is 20 hertz. Again, typically that's if you have really good hearing. As teenagers, you might still have that. I know I don't. We can do a test for that to see if you have that or not. So infrasound's below what humans can hear. And some animals can go below that. Think about cattle, elephants. They can hear below what we can hear. And many animals can hear above, but not so many can hear below what we can. So that's the idea of frequency, how many waves per second, and that creates the pitch. And we create that human hearing range of what we can hear, that high end and low end of what we can human hearing. So to think about that, think about the idea of frequency. So how many waves per second? So here would be a high frequency, lots of waves coming at you at once. And here would be a low frequency, the waves are more spread out. So here we have a low frequency, the waves are more spread out, this would be a lower pitch. This would create a higher pitch. Now, the last two things here, guys, are some ideas of how sound is used or what sound can do. This first one is called resonance. Resonance is the idea that if the frequency of sound waves exactly matches the natural frequency of an object, the sound waves can add to the object's vibrations, creating sound. So believe it or not, every kind of solid, everything kind of vibrates. Those molecules inside, they're kind of vibrating in place at a certain frequency. They're back and forth so many times per second. If we can create sound waves that match those natural frequencies inside those objects, even though we can't see them vibrating, they are. Those solids inside there are still kind of vibrating in place. If we can match those vibrations, we can get things to vibrate and create sound. The classic example of this is probably in cartoons or in some movies. They have the opera singer singing really loud at a certainly high squealy pitch, and it shatters windows or it shatters a glass. And we know this has been proven on Mythbusters. You can actually do this, but that's the idea of resonance. You match that windows, that glass's natural frequency, and if you get it to vibrate, then it shatters, because glass is fairly brittle and it shatters and doesn't take the vibrations very well, so it shatters. And that's the idea of resonance, matching that frequency and amplifying the natural frequency of that object. Our last idea is the idea of the Doppler effect. The Doppler effect is the apparent change in frequency as a wave source moves in relation to the listener. The change in frequency is heard as change in pitch. And this, simply put, is if you ever had a fire truck or a police car drive by you with the sirens on, you notice obviously it gets louder as it gets closer. That'd be the amplitude gets higher, the loudness. But the pitch changes too. As it drives by you, that pitch goes from really high pitched right by you to all of a sudden it kind of drops. The pitch gets much lower as it drives away from you. And that's the Doppler effect. And we can take a look at this here in the next picture. So here, let's say we have our moving belt. This is our fire truck right here in blue, and it's moving this way. What happens is, as it's moving toward you, these sound waves get very close together. So you have a higher frequency, create a higher pitch. Then it drives by you. So the waves behind take longer to get to you, so they're more spread out. This would create a lower frequency, and that pitch will drop. So the Doppler effect explains why moving objects, that pitch doesn't always stay the same. That pitch changes from a higher pitch as it gets toward you, and it moves away, that pitch gets lower. That's the Doppler effect. Alright guys, we're going to stop here for today. I thank you guys for watching, and we'll see you guys along the way.